In chemistry, we have studied the SI-based units, units such as meters, seconds, and grams. Now we are going to add an additional SI base unit. The mole is the base unit in chemistry and in science that measures the amount of a substance. Remember that a substance in chemistry classification of matter is an element or a compound. Those types of matter that have definite chemical compositions. So what is a mole? Well, in actuality, a mole is just a counting number. So what's a counting number? You're actually quite familiar with them. If I sent you to the store and asked you to buy a dozen of eggs, when you open the carton of eggs, you would find, not to your surprise, that you have 12 eggs. So when we say a dozen, you know to count out 12. If I wanted more than a dozen of eggs, I could actually order a gross of eggs. Once in a while, we buy pencils by the gross around here. And so if I get a gross of pencils, that is 144 pencils. Or if it's eggs, it's 144 eggs. If I send you down to Carrie's office and ask her for a ream of paper, okay, this is a ream of paper. In that ream of paper, I know that there are going to be 500 sheets of paper. When we ask about a mole and how much is a mole, if I'm wanting a mole of anything, I am asking for 6.02 times 10 to the 23rd of whatever I am asking for. So what are we going to count in chemistry? What are we going to use 6.02 times 10 to the 23rd of what? Well, in chemistry, we often are counting what we call representative particles. Representative particles, actually, you're very familiar with. They include atoms, ions, molecules, and formula units. Remember, we have the elements of the periodic table and their smallest particles are the atom. If we gain or lose electrons from those atoms, we have ions. If we covalently bond atoms together, we form molecules. And if we transfer electrons to form ions and they bond, we form ionic compounds, which are in the simplest ratio of formula units. So how are we going to use the mole in chemistry? Well, we're actually going to use the mole as a conversion factor. If you recall from earlier in the year, when we did dimensional analysis, we used conversion factors to take units such as grams and turn them into milligrams. We're going to do the same thing with the mole. So what is it exactly that we are going to be converting? Well, if we have a certain amount of substance, X amount of substance in grams, we're going to be able to find out how many representative particles are in that amount of substance. Vice versa, if we have a set amount of representative particles, such as atoms, we can also figure out how many grams of that particular substance that would be found in that many particles. Avogadro, who came up with this number, the mole, the 6.02 times 10 to the 23rd, also gave us another idea that we are going to have to use in our mole conversion, and that is something called molar mass. Molar mass is the mass of an element or compound, but it's a whole mole of that element or compound that we designate. Let me give you an example. So let's see how this molar mass idea works. We can pick any substance, and so we're going to start out with an atom of carbon. We can go to our periodic table and we would find, if we looked for the mass of carbon, that it would be 12. And if we put a unit behind it, we would put the unit AMU, which stands for atomic mass unit. The A standing for the fact that we're only working with one atom. But what Avogadro found in his studies is if we had a mole of carbon, in other words, remember 6.02 times 10 to the 23rd atoms of carbon, that it would have a total mass of 12 grams. Let's do a second example of molar mass. This time we are going to use the substance water, H2O. Remember that compounds have definite chemical compositions and are considered substances. Again, we are going to go to our periodic table and we are going to add up the masses of the elements involved in H2O. So if we look up the mass of hydrogen atom, it has a mass of 1 AMU, and there are 2 hydrogen atoms. Plus, we're going to add in the mass of an oxygen atom. And if we look at the mass of the oxygen atom on a periodic table, its mass is 16. So if we total all that up, we would get a mass of 18 AMUs for our water molecule. Now again, Avogadro said that if I had 1 mole of water molecules, remember our mole being 6.02 times 10 to the 23rd molecules, that it would have a total mass of 18 grams. So our next step is to work conversions. How do we take moles or atoms or grams, and how do we work conversions between those different types of units? When we work dimensional analysis problems, we use conversion factors, and it's very important to remember that conversion factors are always equal to 1. So the 2 pieces of information that we're going to use for our conversion factors are the following. First of all, we know that if we have 1 mole of any substance, it is equal to 6.02 times 10 to the 23rd particles, representative particles of that substance. The second piece of information that we know is if we have a mole of a particular substance, that it will actually equal the molar mass in grams of that particular substance. So one of the conversion factors that we can use when we're working these problems is the 1 mole equaling the 6.02 times 10 to the 23rd representative particles. And we always set it up into a fraction in dimensional analysis. So we can use it as 1 mole over 6.02 times 10 to the 23rd, and then we can pick our unit. We can pick atoms, we can pick ions, we can pick molecules or formula units. But as we know, depending on what it is that we're trying to solve, we can also take that conversion factor and we can flip it over. So we can put the 6.02 times 10 to the 23rd on top, and we can put the 1 mole on the bottom, depending on what type of problem that we're going to solve. Remember that the conversion factor is equal to 1. So 1 mole is really the same as this, and we can flip it around the other way, and it is still equal to 1. Likewise, we can use a second conversion factor. The second conversion factor is if we have 1 mole of a particular substance and we have to designate that particular substance, we know that it is equal to the molar mass of that particular atom or ion or molecule or formula unit, again, depending on what particular substance we're using. Like the conversion above it, we can also take it and we can flip it around the other direction if we need to do so. We can put the mole on top and we can put the amount of grams of that particular substance on the bottom. So now it's time to solve a few problems. So the first problem that we're going to solve is we're going to take 1.5 moles of carbon and we're going to convert that number of moles into atoms of carbon. So in dimensional analysis, we always start with the given number, which is 1.5 moles of carbon. And then we have to pick our conversion factor, the conversion factor that is going to cancel out the mole and take us to the unit of atoms. Now, the conversion factor that we're going to use is going to be one of these two, the mole to particle conversion, but we need to have our moles on the bottom so that the moles will cancel out. And our new unit will be the unit that is on the top, the number of atoms. So positioning our units has to come first. So if we take 1.5, multiply it times the 6.02 times 10 to the 23rd, we would come up with an answer of 9.0 times 10 to the 23rd atoms. Moles would cancel out and would no longer play a part in it. The reason we go to 9.0 is because we have to recall that we have to maintain the number of significant figures. We started out with 2 here, and we need to end up with 2 there. The second problem that we're going to work is the conversion of 2.2 grams of water into moles. This time we're going from grams to moles, so we will not be using the 6.02 times 10 to the 23rd, which deals with representative particles. We are going to be working with the mole to gram conversion. So again, we start out with our 2.2 grams of water. And since we want our grams to cancel out and go to moles as our answer, we are going to use the conversion factor where the gram is on the bottom. And so we're multiplying through and canceling out the grams and going to moles. However, I am going to move this because we're going to put the 1 mole on top and our grams need to go on the bottom. Now these are grams of water that we would find in 1 mole. So this is where we'd have to go to our periodic table and we would have to look up the molar mass of water. Again, a reminder that we're going to look up the mass of the 2 hydrogen atoms. They each have a mass of 1 and oxygen has a mass of 16. So the total mass of 1 mole of water is 18 grams. So we're going to cancel those grams out. Our new answer is going to be in moles. Mathematically, we take 2.2 times 1 and then divide it by 18. And if we put that into our calculators, we will come up with 0.12 moles of water. The third problem that we're going to do is take 3.0 grams of HCl, hydrochloric acid, and we're going to find out how many molecules it is. Hydrochloric acid is a covalently bonded compound, so its representative particle is going to be in molecules. But if you look at the conversion factors that we have available to us, you will note that we don't have a conversion factor that takes us from grams directly into molecules. So we're going to have to set this problem up just slightly different. We're actually going to have to use two conversion factors to get to our answer. So again, we start out with our 3.0 grams of HCl. Now, the only conversion factor that allows us to cancel out our grams is our gram to mole conversion, our molar mass to mole conversion. So we're going to use this particular one where the grams are on the bottom and the mole is on the top. And we're always going to go to 1 mole because we're looking at the mass of HCl in 1 mole. So we're going to go to our periodic table to find out the molar mass. And if we look at the mass of hydrogen, it's 1, and chlorine is about 35.5. So if we add the two together, the mass of 1 mole of HCl is 36.5 grams of HCl. Now we can cancel out the grams, and now we are at 1 mole of HCl. But we want our answer to be in molecules, so that's going to require us to use the second conversion factor. This time we want to be careful that our moles are on the bottom and that our representative particles are on top. So we're going to use this conversion factor because we have 1 mole on the bottom and then our representative particles on top. So we place this in here. And we're in molecules. Our moles are going to cancel, and our new unit answer is going to be in molecules. The last step that we have to do to complete this problem is simply to do the math. We go ahead and we multiply across and then divide by the number on the bottom. After calculating those numbers, 3 times 6.02 times 10 to the 23rd divided by 36.5, we come up with an answer of 4.9 times 10 to the 22nd. We are going to maintain at 2 significant figures because our original number up here had 2 significant figures and we cannot change that. So our conversion factor numbers here are not going to play into determining the significant figures of our answer. The final problem that we're going to work today is going to have us taking 2.2 times 10 to the 22nd molecules of oxygen, O2, diatomic oxygen, and converting it to grams. What this problem is going to show us is how we still use the same conversion factors. Just by simply flipping them around, we can find the answer to this problem. So again, we start out with our given of 2.2 times 10 to the 22nd molecules of oxygen. Now I'm going to be careful here that we don't abbreviate molecules down to MOL because that would be moles, so we have to be very careful of that. Now again, we cannot convert molecules directly to grams. There is not a conversion factor that allows us to do this. So we have to pick the conversion factor that has molecules on the bottom, which is this one. And that's the 6.02 times 10 to the 23rd molecules of O2. And of course, that is the number of particles in 1 mole of O2. So now we've canceled out the molecules. The next step then is to take our mole of oxygen and convert it to grams. So if we take our 1 mole of oxygen. We know that we want moles here, and we're going to grams. This conversion factor right here is the one that we want to use. So we're going to look at 1 mole of it, but now we need to find the molar mass of our O2. If we go to the periodic table, the mass of oxygen is 16, and since there are 2 oxygen particles, its total mass would be 32 grams. Again, we cancel out the moles, which leaves us with our unit right here of grams. So now all we have left to do is the math. We simply take our 2.2 times 10 to the 22nd, multiply it by 1 times 32, and then divide it by 6.02 times 10 to the 23rd. After calculating the setup of this problem, we find out that our answer is 1.2 times 10 to the 0 grams, which is the same as 1.2 grams of oxygen. This is our final example. Happy mole conversion, and don't be afraid to ask your teacher for help. Thank you.